In this video, we go over Frostman measures, which are a useful technique for estimating the Hausdorff measure and dimension of a set. So let's go over an example. Suppose we're trying to estimate the dimension of a Cantor set. So recall that a Cantor set is constructed as follows. We start with the unit interval from 0 to 1, and that's our set E0. Then we remove the middle third of this set. So now we have two intervals of length 1/3. And then so that's E1, we construct a new set E2 that we get by removing the middle thirds of those intervals. So now we have intervals each of length 3 to the minus 2, so 1/9, and there are 4 of them, or otherwise 2 squared. And then we continue this process, and the intersection of these sets is a set E. And so we claim that the dimension of E is equal to log 2 over log 3. So first we'll prove the upper bound, that the dimension is at most log 2 divided by log 3. So notice by the construction, so E is contained in the intersection of all these sets. So in particular, E is contained in 2 intervals of length 1/3, and it's also contained in 4 intervals of length 1/9. And by induction, we can show that E is contained in 2 to the n intervals, each of length 3 to the minus n. So when we compute the 3 to the minus n s measure of E, okay, so recall that this is the infimum over all coverings of E of sums of the following form as we range over sets ij that cover our set E but have diameter less than 3 to the minus n. So by definition, this quantity is at most this sum. But notice that each of these intervals has the same length, 3 to the minus n, and there are 2 to the n of them, so it's equal to this. And by our choice of s, this is equal to 1. So thus, the Hausdorff measure of s is equal to the limit, as n goes to infinity, of these hs 3 to the minus n measures, and we've just shown that that is at most 1. So because it has finite s-dimensional measure, that means that the dimension is at most s. Now, estimating the s-dimensional Hausdorff measure, or Hausdorff dimension of a set from below, is a little trickier to do by hand. What's easier to do is to show the existence of an s-dimensional Frostman measure. So this is a Radon measure with compact support, such that the measure of any ball is at most a fixed constant times the radius of the ball to the power s. So the connection between Frostman measures and Hausdorff measure, and hence Hausdorff dimension, is given by the following lemma. So suppose that mu is a Frostman measure, and let's say that the constant c involved is equal to 1. Then for any set in my metric space, the Hausdorff measure A bounds from below the hs infinity measure of A, which is at most the Hausdorff measure of A. So recall that, so hs infinity, this is the hs delta measure of a set when delta is equal to infinity. Okay, so in other words, this is equal to the infimum over the sums of diameters of sets to the power s, so that the union of EI contains my set, and there's no restriction on the size or diameters of the set EI. Sometimes this quantity is called the s-dimensional Hausdorff constant. So let's go through the proof real quickly. So let EI be a collection of sets that cover my set A. Now I'm just going to pick some point xi in EI, and then I'm going to let BI be the ball center at xi of radius equal to diameter of EI. So notice that because the radius of this ball is at least the diameter, that means that this ball contains the set EI. So thus, the mu measure of A is at most the sum of, so notice that because each of these EIs is contained in a BI, these BIs also cover the set A. So that means by subadditivity, the measure of A is at most the sum of the measures of these balls. Now, by the Frostman property, this is at most the radius of each of these balls to the power s. but the radius of these balls is exactly equal to the diameter of EI to the power S. And thus we've shown that for any covering of the set A by sets EI, the sum of the diameters of the EI's to the power S is at least mu A. So taking the infimum over all such coverings implies that the measure of A is at most the Hausdorff content of A. And then recall the Hausdorff measure is the limit. So this is less than or equal to HS delta of A for all delta bigger than 0. And as delta goes to 0, this increases to the Hausdorff measure of A. So let's revisit the example of the Cantor set. I'm going to now derive a lower bound for the Hausdorff dimension of the set E naught. And the way I'll do that is by constructing a sequence of Radon measures that will converge weakly to a Frostman measure of the appropriate dimension. So the way I'm going to define this Frostman measure is that I'm going to define it to be a so I'm going to define each Frostman measure to be a constant multiple of Lebesgue measure restricted to each set in the stage of the construction of the Cantor set. So mu naught is just going to be a constant multiple of the characteristic function of E naught, the unit interval, and I picked the constant to be 1 just so that the measure of the unit interval is 1. So next, I define a measure mu1 that will be a constant multiple of Lebesgue measure restricted to the two intervals that comprise E1, and I pick that constant so that the measure of these two intervals is 1/2. And so on. If I take mu2 to be a characteristic function of E2, I pick a constant so that the measure of each of these intervals is 1/4. So notice that as I look at the sequence mu0, mu1, mu2, etc., as k goes to infinity, for k large enough, the measure of any interval will remain constant. So for example, if I look at this interval here, all right, this had mu1 measure 1/2, and then if I compute its mu2 measure, notice that the two intervals in E2, there are two intervals in E2 that are contained in E1 of measure 1/4, and those sum up to 1/2. Okay, so that means that for any fixed interval in one of my sequence of sets in the construction of the Cantor set, for k large enough, the mu k measure of that interval will be fixed. So for all I in construction of E, mu k of I, and we can actually compute what it's going to be. It's going to be L of I to the power S, where S is equal to log 2 over log 3. So you can verify by the construction of my measures mu that this equality will hold for k large enough. So now I take a weak limit. These will converge to a measure mu, which is now Frostman. So one can show that for any interval I, that mu I is going to be at most some constant times the length of I to the power S, or in other words, the diameter of I to the power S. And thus, this is a Frostman measure supported on my set, which implies that the dimension of E is at least S. So there's actually a converse to this result that says if I have a Borel set of positive Hausdorff measure, then there exists an S Frostman measure with support contained in A. More specifically, I can find a Frostman measure mu with constant 1 of dimension S, and so that its mass is at least a constant times the Hausdorff content of A. I'm going to briefly go over the construction of the Hausdorff measure for the case of A, a subset of the unit cube compact. Okay, so the algorithm goes as follows. Okay, so I'm going to let delta m of q equal, delta m of A denote the dyadic cubes in delta m. So recall delta m is the set of dyadic cubes of side length 2 to the minus m, such that they intersect A. Okay, so what I do is that for each cube in delta M, I define a measure mu m. This will be a constant multiple of Lebesgue measure restricted to the cubes in this collection, so that for any cube in this collection, the mu m measure is equal to L of q to the power s, where L of q denotes the side length. So next, I go one level up. Now I look at cubes in delta m minus 1. So for cubes in delta m minus 1, I check if my mu m measure of q is, if it violates the Frostman condition. So I'd say if now, when I check this cube, the mu measure is strictly bigger than the side length of q to the power s. Okay, if this is the case, then I rescale my mu measure, at least inside this cube, such that mu m of q is now equal to L of q to the s. Okay, now if this inequality is not violated, then I leave the measure alone. Okay, so I readjust my measure as I go along. And then I do this for the next level up, so I look at cubes in delta m minus 2 and perform the same procedure. And then once I get to the top cube, the unit cube, I now have a measure mu sub m such that it satisfies this inequality, that mu of m of q is at most L of q of s for all dyadic cubes, q and delta, with side length at least 2 to the minus m. So in other words, this is a Frostman measure up to scale, up to the mth scale. So if I want a Frostman measure that is Frostman for all scales, so for all cubes, what I do is, because these measures have compact support and a uniformly bounded measure, I can pass to a subsequence so that they converge weakly to a measure mu. And this measure mu will be Frostman. So in fact, it will be less than or equal to side length of q for all dyadic cubes, q to the s. Okay, and one can show that this measure has positive measure, and in fact, the measure of A is comparable to the Hausdorff content of the set A. So recall in the construction of an S-dimensional Frostman measure, the way the algorithm worked was that for every cube that I found where my measure was violating the Frostman inequality, so that corresponds to a place where my set is distributed in more than an S-dimensional way. And whenever I encounter such a cube, I suppress the density of my measure. So here I've simulated a few examples of Frostman measures generated for the same set, but for different dimensions. So the set that I picked is a bunch of randomly selected points near the center of a square, plus a line passing through that blob of random points. So in this example, we have points distributed in several different ways. Near the center of the blob, points are distributed in almost a two-dimensional fashion. Along the line, they're distributed in a one-dimensional fashion. And then there are many isolated points around the blob that are sort of correspond to a very small dimensional distribution. So in the first example, I've simulated a 0.1 dimensional Frostman measure. So this is going to have small density in places where the points are distributed in more than a 0.1 dimensional fashion. And as we can see, the places where the density is large are exactly around the isolated points, where things are very small dimensionally distributed. In the next example, I simulated a 1 Frostman measure. So this is going to be small in places that are distributed more than one dimensionally. So now we see that the density is large along the line, which is one-dimensional, and also at these isolated points, but near the center of the blob, because it's still distributed in a almost two-dimensional fashion, the density is very small. Now here I have a 1.5 dimensional Frostman measure, so now the density is starting to pick up near the center. However, you'll see that it's still large around the boundary of this blob, where the points are not as concentrated as in the center. And finally, if you look at the last example, this is a 2 Frostman measure, and this just returns Lebesgue measure restricted to the characteristic function of the set. The reason being is that in the proof, you'll recall that I changed the density of my Frostman measure whenever the Frostman inequality was violated. But in the case of d equals 2, if we're working in the plane, that when I define my first Frostman measure at the bottom scale and I start moving up in scale, the Frostman inequality will always be satisfied. So I'll never actually change my measure, and so the density remains constant, and that's why I have the same color all throughout this figure.